Okay, so we have looked at both future value and present value of an annuity, and now we're going to move on and look at the regular payments. So we're going to be calculating our regular payments now. So to be able to do this, we need to figure out whether we are talking about future value or present value in an annuity to know what formula we're going to use to be able to figure out our regular payments. Okay, so we use the amount formula, the future value formula, to determine the accumulated value of the regular payments at the end of an annuity. We use the present value formula to determine the money needed at the beginning of an annuity to provide regular payments. When we know the amount or present value, we can solve for the regular payments by rearranging the formulas. Okay, so first we're going to look at examples, and we're going to determine whether we're going to use the future value or amount formula, or we're going to be using the present value formula. So first one, Stephen plans to repay his student loan of $15,000 by making equal annual payments. Okay, so we want to think if we have a present value with the future value being 0, or if we're starting off with $0 and we are going to have money in the future. So here, Stephen is starting off with a loan of $15,000, and then he's going to pay that off, so the future value is going to be 0. So this means we would use the present value formula for this, for A. Okay, B, Winnie saves $5,000 by making equal weekly payments at her bank. Okay, so we think about that. Winnie saves $5,000, and that's at the end, starting with $0, and after making those weekly payments, she has the $5,000. So that means this one's going to be future value. Okay, C. Sergio plans to retire a millionaire by making equal monthly deposits into his retirement savings plan. So this is at the end, having money. You're starting with nothing and you're investing that money to then be a millionaire at retirement. Because there is going to be a $1 million future value, then that would be the formula we would use here. And last one, Veronica plans to make equal quarterly withdrawals from her $300,000 retirement income fund. Okay, so that's starting with money and making withdrawals from it until there's nothing left. So this one is present value. Okay, so we're going to be looking at situations like this where we need to determine first whether we're using present or future value, and then we can rearrange those formulas to find out what the payment would be. So Sophie wants to travel for a trip to Europe following graduation in 4 years' time. She predicts the trip will cost her $5,000. What regular deposit does she need to make every 6 months in an account that earns 5% interest compounded semi-annually to achieve her goal? Okay, so the first thing we want to determine is whether we're going to be using our present value or future value formula. Sophie's going to start with $0, and she is going to be saving money by putting deposits into her account to have that $5,000 at the end. So that means we want to use our future value formula here. Okay, so that formula is A equals R times 1 plus I to the exponent n minus 1 over I. Okay, so we need to figure out what the values are in our equation, and then we can rearrange. So we have A, R, I, and n. So A is the amount of money, the future value that we want to have, and that's going to be the $5,000. We don't know how much she's going to deposit every 6 months. That's what we're figuring out. So we need to find out what that R value is. Okay, our interest is 5%. We need to change that to a decimal, so we divide by 100. And then we divide that by our number of compounding periods. Semi-annually means twice a year, so dividing that by 2. Okay, so 5 divided by 100 divided by 2 gives us 0.025. And our n value, it's going to be our number of years, which is 4 years. And it's being paid every 6 months or semi-annually, so that's times 2. 4 times 2, so our n value is 8. So we can put on all the values that we know. Our A is 5,000. Our R we don't know. And 1 plus 0.025 to the exponent 8 minus 1. And that's over 0.025. Okay, so the first thing we can do is move this divide by 0.025 to the other side and multiply it. So it'll be 5,000 times 0.025. And we keep the other side with what's left over. Okay, that's 125. And now we want to get R by itself, so we're going to move all this other piece. It's R times this full bracket. So when we move this full bracket to the other side, it's going to divide over here. So 125 divided by 1 plus 0.025 to the exponent 8 minus 1. And that's our regular payment. Okay, so dividing by that value. We are going to get $572.34 as our regular payment. Okay, so that's how much that Sophie will need to deposit every 6 months. Looking at our next example here, John borrows $6,000 to buy a car. He will pay back the loan monthly over 3 years at an interest rate of 12% per year compounded monthly. What would his monthly payment be? What is the total amount John repays? And how much of the amount repaid is interest? Okay, so a few questions to answer here. We're starting with an amount of $6,000. The future value will be 0 because it will be a loan that's paid back. So since we're starting with the 6,000, that means we need to use the present value formula here. Okay, thinking about all our values, our present value is the $6,000. We don't know how much the monthly payment is going to be. That's where we're finding out. Our interest is the 12% put into a decimal, so divide by 100, and divide by our compounding, which is the monthly, so that's 12. So 12 divided by 100 divided by 12 gives us 0.01. And our n value is our number of years times our compounding periods. So 3 years times 12, our n is 36. Okay, so for A, we want to know our monthly payment. We're going to use the present value formula. Present value is r times 1 minus 1 plus I to the negative n over I. Our present value is 6,000. Our r we are finding out, 1 minus 1 plus 0.01 to exponent negative 36 over 0.01. Okay, so the first thing we do is we take that divide by 0.01, bring it to the other side and multiply. So 6,000 times 0.01 is 60. And then we need to take this bracket here, move it to the other side, and we'll divide that. So it'll be 60 divided by the 1 minus 1.01 to the exponent negative 36. And we get $199.29 as the regular payment we need to make. Okay. Question B is asking what the total amount John repays. So we know that each payment that John makes is the $199.29. We also know that he makes 36 payments. So for B, the total amount is going to be the $199.29 times 36. So the total amount that John repays is $7,174.44. Okay, and the last one is asking how much of the amount repaid is interest. So if John pays a total amount of $7,174.44 and the initial loan is only $6,000, we are going to subtract those two to figure out how much interest he actually paid. So our interest is 7,174.44 minus 6,000. And that's $1,174.44 interest that John paid. Okay. Looking at one more question here. And this one we are going to be using the TVM solver again. So Shahrzad starts a savings program to have $23,000 in 10 years. She makes deposits at the end of each quarter in an investment account that earns 6.2% per year compounded quarterly. Determine Shahrzad's quarterly deposit is the first question here. So, she wants to have the $23,000 at the end of 10 years, meaning she's starting to save money. The present value will be 0. The future amount will be the $23,000. Okay, this is 10 years, and quarterly means we are timesing by 4. So 10 times 4 gives us our end value as 40. Our interest is just a percent, the 6.2. Our payment is what we're figuring out. And our payments and our compounding periods per year is 4 because it's quarterly. Okay, so putting those values into our solver here. 40, 6.2, present value is 0, future value is the 23,000. And our payments and our compounding periods is 4. So then we can hit solve for PMT. And we get $419.36. Okay, so the quarterly deposit that she has is the $419.36. Okay. So for part B, does Shahrzad's deposit double under each change? So we're just going to make slight alterations to our values that we already have here. The first one is saying that the amount is twice as great. So we want the future value to be the 46,000 instead of the 23. So changing that value, everything else will stay the same, and we're going to solve for the payment again. And that payment becomes $838.72. Okay, so it's asking if the deposit is doubling when we double these certain values. So, does it double? 838.72 divided by 2 does give us the 419.36. So, it does double when we change and double our future value. So our deposit doubles when our future value doubles. Now looking at the interest rate, if we double the interest rate, keep everything else the same. So I'm going to change this one back to the 23. And we're going to change this one to 12.4. Press our solving for the monthly payment again. And we get $298.18. Okay, so when our interest is doubled, then our deposit amount does not double. Okay, so because we're earning more interest on our money, then we wouldn't have to deposit as much at each quarter. And the last one is talking about doubling the time. So going from the 40 payments to 80 payments. Okay, everything else staying the same, changing our N to 80 and looking at our monthly payments is $147.14. Okay, so we see that our deposits just double when our future value doubles. Okay. So same thing goes with the TVM solver. You're determining whether you are dealing with the present value or future value to know where that amount goes. And the other one will be 0, and you're working to solve from there. Okay, so here are the textbook questions for today. You'll be doing some using the formula and then other ones using the TVM solver. Let me know if you have any questions.